Today, we are moving away from lighting systems, which was our first actual system type that we looked at in this course. And now we're going to move to another relatively simple system in domestic hot water. So what the heck is domestic hot water? I mentioned it on day one, I think, but essentially this is anywhere you're going to have hot water in your building that is used by the public. So hand washing in sinks and showers, that is all fed off of a domestic hot water system. And we all have one of these heaters in our homes. Or if you live in an apartment, you might not have a dedicated domestic hot water heater for your specific apartment, but there has to be one somewhere in that complex. Otherwise, you wouldn't be able to take a shower. So this is something that is in pretty much every single building that you can imagine. They're typically either straight electric resistance heaters, which would be a 100% efficient system, or I would say more commonly they're natural gas, although that is a trend that is shifting as we're trying to get away from natural gas fuel sources. Historically, though, gas heat on these heaters has been more popular, and that might raise the question, well, if electric if the electric heater is more efficient, why are more of these heaters gas fired? Something we've talked about several times now. Natural gas is about a third of the price on a per BTU basis, even accounting for that reduction in efficiency by going to natural gas, it is still considerably cheaper. The domestic hot water load and the percent of the total energy use. I'll bring up the CBEX usage energy pies here in a sec. This is a energy use that varies all over the place, depending on what type of building you're looking at. If you have an education building, it makes up about 8%. That's a decent chunk of the pie, not as much as HVAC or lighting, but it's right behind lighting at 9%. In an office, though, it makes up a much smaller percent compared to education. The main reason being, in an office, you don't have any showers or anything, whereas in a school facility, you would. In food service, it makes up a decent chunk, which makes sense if they're um, using it for, say, washing dishes or something. In healthcare, makes a big percent too, because they have a lot of cleaning they have to do. And then the big one, though, is in lodging at 24%. And that makes sense. If you think of a hotel, there's not a lot in a hotel that's going to use a lot of energy. I mean, and a lot of times, most of those hotel rooms are empty, but you do have a lot of people taking showers. And so that's why that makes such a big chunk of the total energy use pie. A basic domestic hot water system, these are very simple devices. So that heater on the left, that's a basic gas-fired water heater. The way you can tell is this yellow line coming into the heater. This is the gas line coming in. This little leg here at the bottom is called a dirt leg or a sediment trap, because that gas can sometimes have some dirt particles in it. And this essentially, just by momentum, forces that dirt to collect in this little leg here. And there's also a flue out here on the top that after the gas is combusted, we have to get rid of the products of combustion. So this would tell me it's a gas-fired water heater. But basically how it works, you bring in cold water from the city, usually around 50 to 55 degrees, which is relatively cold. You throw that into the tank. You have a gas or an electric heating source that's going to heat up this mass of water. So you store it in there, and then you have your hot water out, at 120 to 140 degrees. And that is just going to get delivered out into the space as people in bathrooms or showers, as they open valves, the hot water is just going to flow just by nature of the pressure. You're giving the water somewhere to go. The domestic hot water load, so this could be defined as the amount of energy needed at the end use. The end use being a sink or a shower. That's where it's actually doing something useful for the person who is needing that hot water for something, whether it's taking a shower or washing their hands. And you should consider your load to be your output in your efficiency equation. So efficiency is driven by our input and our output. The load is equal to the output of that equation because the load is independent of any efficiency. If I need 5 gallons of hot water, that has a certain energy component to it that has to be delivered at the end. And that really doesn't care what's going on with the efficiency of the heater. And this goes back to a common refrain that the engineer who taught a lot of the courses in my master's program that I took, this is something he said a lot. The load is the load. It doesn't care if your water heater is 100% efficient or 50% efficient. The load is the load, and that's the bottom line. It only cares about what it needs to be happy. In that example I just used, if I need 5 gallons of 100-degree water, that is the load. You can express the load in any energy unit: BTU, kBTU, therm, MMBTU. It's very common to express it in terms of therms because that is what is most commonly what is billed by the utility companies. And then our energy input, what we actually pay for from the utility, is our load divided by whatever the efficiency of our heater is. And I'll run through an example on that. Your load can be highly variable. What if people go to the bathroom all the time? Or what if you have an event center and there's a whole string of high occupancy events in that week? Best we can do is estimate it, which I realize I've been saying a lot throughout this course. When we're talking about plumbing fixtures, sinks, showers, toilets, well, not toilets, we'll come back to that. Sinks and showers, typically those fixtures are expressed in GPM, or gallons per minute. That's how much water is going to flow through those per minute whenever water's running. Toilets, on the other hand, typically are expressed in gallons per flush because a toilet's not something that you just continuously run as you need it. You just push the button and it goes. But with toilets don't have a heating component, or at least you shouldn't be using domestic hot water to flush your toilets. There's absolutely no reason to. So technically, toilets are not part of the domestic hot water system. If we're going to calculate our load, first we need to figure out how many gallons of water are going to be used, and then we can take that and figure out how much energy it will take to heat it up to whatever temperature we need to deliver it at. And the basis of this equation is this old heat transfer standby. Actually, I think I remember using this equation in chemistry. So this equation shouldn't be any surprise to you. But Q, our heat transfer, is equal to M, our mass, times our C sub P, which is our, what's the term, heat capacity of our fluid, and then the delta T. What's the temperature difference that we're seeing? Let's run through a quick example. The architect tells you they're designing this building to have 100 occupants, and there are some rules of thumb about how often individuals in that building are going to use those restrooms. Let's say 3 times a day for every occupant. And whenever they use the restroom, they wash their hands for 30 seconds, or at least we can hope they're washing their hands. The sinks that we are putting in, you pull up the specification sheet and you see that these are 2 gallon per minute sinks, or faucets rather. And we know the water is going to come in from the city at a nice cool 50 degrees Fahrenheit. And we know we want to deliver it to the sinks at 120 degrees Fahrenheit. And we are going to put in a domestic hot water heater that's 80% efficient and it's gas fired. So step one, we need to figure out how many gallons of water are going to be used. So we have 100 occupants. We know, or are assuming, 3 uses per occupant per day. When the sinks are running, they're running at 2 gallons per minute. They're using them for 30 seconds, which, to keep the units right, minutes to minutes, half a minute per use, 365 days a year. If it was an office building, maybe you could argue that it's only used 5 days a week. And so you would reduce the days per year that you would run this calculation for. So it comes out to 109,500 gallons of water per year that are going to be used in these restroom sinks. We figured out the gallons now, and now we can go to that MC delta T equation. So the mass component of this equation, gallons per year, water has a density of 8.33 pounds per gallon. So that brings our units to gallons for our mass term. The I think I called it the heat capacity, but now I realize it's the specific heat of water is 1.0 BTU per pound per degree Fahrenheit. And then our delta T, 120 minus 50. So what we need for an output from our heater is close to 64 million BTUs per year to serve the load. And we haven't factored in any efficiency of our heater yet, because the load is the load and the load does not care what's serving it. It just knows what it needs to get the desired output at the end. So if that's our output, we can figure out the input. We take the BTUs, convert it to therms, because that's typically how the utilities like to bill us. And then we divide by our heating efficiency, because our input should always be greater than our output. If you multiplied by 0.8, you'd end up with a lower value, not a higher value. 64 million BTUs sure sounds like a lot, but really that's only about 800 therms per year, which is really not a lot. That's not a very large gas load. Running through this example is another clear example of how using the equation functions in office applications can be helpful with units. So I can see, okay, occupancy cancels with occupancy. I can run through this and see that all of my units cancel out to give me gallons per year on the back end. And same with the MC delta T. All my units should cancel out to give me BTUs per year. Let's discuss some ways we can save energy with these systems. There's not a lot to these systems. They're another very simple type of system, kind of like lighting. Well, it's really not like lighting at all, but they are very simple. One of the most basic things you can do is install some low flow fixtures. So you go in, you tear out the old fixtures, and you put in new fixtures that are going to use less water. So if you found an old shower head or a number of shower heads, say in a locker room of a big high school, there could be a number of these shower heads, and you find that they're all 2.5 gallon per minute heads, you can replace those with 1.5 gallon per minute heads. And right there, that's let's see, that's a 40% reduction. And they make shower heads now that even though you're cutting the water flow by, say, 40% in this case, they've designed the heads in a way that the water comes out to give the perception to you that more water is coming out, which is kind of interesting, I think. Toilets, those are a no-brainer to replace with a low flow fixture because people flush them and then they leave. They're not sitting there having to hold the flush button until it's done like you do with a sink when you're washing your hands. Faucets, though, these are a little trickier because the use is dependent on the user. In that previous example, we were assuming 30 seconds per hand wash, but you could ask the question of, well, if less water is coming out of the faucet, do we think that people will wash their hands for longer? If I cut the water flow by 40%, is my time factor going to increase by 40%? Well, there might be some of that, but people do tend to get by with less water than they really think they need. So if you're doing your calculations, you can what's called derate your savings if you think people will use those sinks and showers longer. Just to be conservative in your calculations and to just make sure you're not going to overstate your savings. So maybe you reduce the flow by 40%, but maybe you increase the use time by 5 seconds or whatever you think you're comfortable doing. The basis of savings here, you have that reduction in heating energy for that reduced water flow. In that MC delta T equation, you are reducing the M part of that. And the heating savings are going to be directly proportional to the change in flow. So with that 40% reduction with those shower heads at the bottom, that would equate to a 40% reduction in energy use, assuming the same runtime. And there are some bonus savings here. You're also saving on water. So you're saving 40% or whatever on your water. And while water is not considered energy, it is something that the customer has to pay for. And so you can make a financial case to say, well, you're going to save this much money in your energy use, and you're going to save this much money on your water use reduction. Another basic thing you can do is insulate your piping throughout your building. You heat up that water, and then it gets delivered out into the pipes throughout your house or your building or wherever your heater is. And that water is going to be warm. So if the water goes out at 120 to 140 degrees, and then all of the faucets shut off, now the water just sits in the pipe and it's going to lose heat to the space. Anytime you have a hot thing, anything, it's going to lose heat to the surrounding space if the surrounding space is at a colder temperature. And I can tell you, we are not maintaining our rooms at 140 degrees. So it's a very basic thing and an important thing to insulate all your pipes to prevent this distribution losses. And that's where the basis of savings come from. Reduce distribution losses just from that hot water sitting or even running through the pipes. If you're running water through the pipes, it's still going to lose that heat before it gets to the sink or the shower. You could also do a fuel switch. If your customer has an electric resistance water heater, you can go to a gas water heater. And technically, that is less efficient, but because of that lower cost per BTU, the bottom line at the end of the day, you're going to save money. So the energy use is expected to increase, but the reduction in the cost of energy is going to more than offset that. But like I said, there's a movement right now to push toward what they call the electrification of the utility grid, meaning utilities more and more are trying to push people away from using gas sources and move them towards using electric sources, which brings me to another technology. You could go from an electric heater or a gas heater for that matter to a heat pump. We've talked about heat pumps before. It's using a refrigeration process to take heat from the surrounding air and pump it or move it somewhere where the heat is wanted. If you're going from an electric resistance heater to a heat pump, we're still using the same, I put fuel in quotes, we're using electricity, which isn't really a fuel, but it is an energy source. An electric resistance water heater has a 1.0 COP. It's 100% efficient. If you go to a heat pump, you can get more like 3 to 4 COP. So you're still using electricity, but you can get significantly better coefficient of performance out of a heat pump. And so ultimately that is going to save you energy on your domestic hot water. This is what a basic heat pump water heater looks like. So to walk through the steps, this top component of the heater, which is exploded right here, we're going to pull the surrounding air in just from whatever space that heater is sitting in. Maybe it's just a mechanical room in the corner of the building. It says hot air in, but really it could just be moderate temperature air. Could be 75-degree air. Doesn't necessarily have to be hot. Then you have a compressor in here that runs the DX refrigeration cycle, which transfers transfers heat from the airstream into the water in the tank. And then you end up with cold air out the other side because the heat pump has taken the heat out of the air. And now that cold air out is essentially just rejected air at the end of the day. You could go with a gas-fired condensing hot water heater. Anytime you have a gas-fired heating source, you're always going to have some of that waste heat that is just a natural consequence of combustion that just needs to get dumped outside. Normally, gas heating sources are about 80% efficient, which means 20% of the heat content you just get rid of and you dump it outside. But there is a way to do a little better than that, and that's with a condensing hot water heater. And what these heaters are able to do is capture some of the waste heat that's in the flue water vapor. When the heater combusts gas, it produces some waste gases, and within those waste gases is water. And that water is decently warm. It's a water vapor, so it's not like we're pumping out water or anything like that. These condensing water heaters are able to capture some of that waste heat. A non-condensing or a standard heater is around 80 to 85% efficient. 85% seems like that would be on the high end. Maybe more like 82 or 83 would be normally what we would see. But with a condensing heater, we can get upwards of the 90 to 95% efficient. And we can close a lot of that gap toward making this almost 100% efficient. You're still losing some of those waste gases, 5 to 10%, but it's quite a bit better than a standard water heater. The basis of savings: improved heating efficiency, which means you're going to use less gas. There will be more to come on condensing gas-fired equipment. When we get into hot water systems, not domestic hot water system, but um, building heating hot water systems, we're going to talk more about condensing boilers, and we'll talk more about specifically how those work to get that extra efficiency. You could go with an instantaneous water heater. These are also known as tankless water heaters. Most domestic hot water heaters are that storage type that we're used to seeing in all of our houses. So they store, say, 50 gallons of water, and they heat that water up slowly to get up to whatever temperature we want, and then they just store it until it's needed. The advantages of this storage type: you can get away with a much smaller heater because of that, because of the fact that we are heating the water up slowly. We're not sizing the heater for that peak BTU per hour load. And usually this is using gas heat, which is going to be less expensive per BTU. The downside of a storage heater is if you use too much hot water in a short amount of time, say everyone in your family decides to shower back to back to back, eventually you're going to get all of the hot water out of that tank, and you need to wait while that heater recovers that thermal storage, because it just can't produce that hot water on demand. Which brings us to the alternative option: is an instantaneous heater that doesn't have a storage component and can only heat on demand. The advantages: you're always going to have hot water. Even if everyone decides to take 30-minute showers over 3 hours, you're always going to have that hot water available. The main downside is the heater has to be substantially larger in order to do that. And often these are electric heaters, which means they're going to be more expensive per BTU. They do make gas ones, usually in larger heater sizes, like if you were going to install one of these for a larger building. But if you're talking about a dedicated instantaneous water heater for, say, a couple sinks, it's going to be much smaller. It's going to fit right underneath the sink. Those are typically going to be electric. The basis of savings, potentially, is you're going to have reduced storage losses because you're not storing that 50 gallons of water, which is constantly losing heat energy to the surrounding space, which is what you'd see in a typical storage water heater. You're constantly going to be losing that heat. But you have to consider it might cost you more to go from gas to electric if you go to an electric instantaneous heater. But there might be some other reasons why you would want to go this route. Let's say you have an isolated room that is very far away from where that heater is, and you want to add a sink or add a shower, and it's just um, way too much of a challenge to tie that into the primary water heater. That might be a good use for a dedicated tankless heater. Or maybe you add a room that the existing heater is not sized to serve. Well, I sized this heater for only one shower, and if I add that second shower, I'm not quite comfortable doing that. So that could be another potential reason. To give you an idea of what these heaters look like, so here we have an electric heater on the left side. These U-shaped things are the elements. So that's the electric resistance heaters that are heating the water that's in these storage tanks. If you have a gas heater, you can see there's a very clear separation between uh, kind of an upper chamber and a lower chamber. So the water fills up the storage on the top, gas heat burns on the bottom. An instantaneous heater would look more like this, and this is actually a gas instantaneous heater. But the big difference here is there's no storage component of the water. So what happens is you have your cold water coming in from the city, and as soon as someone opens the hot water on this faucet, the water will start flowing. As soon as this flow sensor sees that there's water flow, that's going to turn on the burner. And this is just a combustion fan just to help with that combustion, make sure that has combustion air. And you're going to have a heat exchanger. And the big difference here is this instantaneous heater only gets one shot. So it kind of wraps around and gets warmer and warmer until it gets to the end. By the time it gets to here, it needs to be up to temperature. And so that's why you need such a larger heater on this. To illustrate it another way, if you have a storage heater, you're going to have that constant heat loss to the space compared to the instantaneous one where there are no storage losses to speak of. But the big thing here is you notice a very large disparity in how big the heater is. So the storage type in this example, 200 MBH, which is 200,000 BTUs per hour, compared to an 800,000 BTU per hour heater on the instantaneous. Just because, again, this gets one shot. By the time it gets from this side to this side, we need to be up to temperature, which is not how this storage system is going to work. Next up, this one's kind of cool. You could put in a solar domestic hot water heater. And when I say solar, I am not talking about photovoltaic or PV solar panels. A solar water heater has nothing to do with electricity. It's not generating electricity. It's not plugged into your panels to offset energy use. No, this is different. I'll have a picture here in a minute to help illustrate this, but you have two sides of the heater that are connected with a heat exchanger. The collector side, this is the side that's going to be outside, that is a panel, not a PV panel, but just a solar collection panel that's just taking heat energy from the sun. That collector side, the panel that goes somewhere up on your roof, that has water going through it, and that gets heated up, and that's where our heat is ultimately coming from. And you do need freeze protection for that, because in the winter months, it could be potentially very cold and you need to protect that water. And then you have the load side at the house. And this is what is actually getting delivered into your house or your building, wherever this is. So to help illustrate this, this would be a basic schematic of what a solar water heater would look like. We have our load side, which is our cold water coming in and our hot water to the house. This is our collector side. This is where our heat is ultimately coming from. So you bring in cold 50-degree water from the city, and that goes into this tank that surrounds this coiled heat exchanger. And then you notice there's a pump on this side, and this pump will turn on and move water into the panel where it comes back down through the heat exchanger and just keeps recirculating on that side. So you can see that that side of this system is an entirely closed loop. and the water running through there can get very hot. So right around 150 degrees Fahrenheit. And that heat energy is just coming from the sun. So if you're sending that 150-degree water through this heat exchanger, quick side note, it says it's a double wall heat exchanger, and that is important because um, basically that just means this heat exchanger has 2 layers of protection, so that if one of those layers fails, you are still protected and you're not mixing the water. Because what you don't want to happen is the water from the collector side to mix with the water on the load side, especially if on the collector side, I mentioned there has to be some freeze protection means. Normally how they do that is they add propylene glycol, which is essentially antifreeze, into that fluid at about 20 to 30%. And that's certainly not something you want to drink. So the cold water comes in 50 degrees, gets heated up through this heat exchanger with super hot water, and then we can leave at around 120 degrees to our sinks and showers and whatnot. So kind of a cool technology. I have yet to actually see one of these pan out and be installed, but it's always kind of intrigued me. The thing that's kind of cool is this is almost free energy. The only component of that system that uses energy is that pump that's moving the water on the collector side. That's it. You typically do need to combine this with a storage tank, just because there's still going to be load when that sun's not shining. So ultimately, you can heat and store that water for use later. And even if you decide to shower later on in the evening, hopefully you still have some hot water in that tank, even if the sun doesn't happen to be shining right at that moment. That said, you most likely, well, maybe not most likely, but you will need to consider possibly still putting in a backup electric or gas heating system. This is going to be kind of climate dependent. If you're in a climate where you just get sun all day long and maybe you just install some very large storage tanks, maybe that's all you need to do is provide this solar water heater. But you don't want an angry customer at the end of the day saying, hey, I ran out of water and it's just been a really cloudy week and it just has not been able to keep up. But ultimately, at the end of the day, this will reduce their gas or electric heating energy. The last topic, the last thing you could consider doing with this system to save some energy is to lower the domestic hot water temperature set point. Meaning, what temperature is that thing set at to deliver out to your sinks and showers? Most water heaters today, they are set to 140-degree water. But do people really need water that warm? Water starts to scald at about 120 degrees Fahrenheit. So 140-degree water seems pretty excessive unless there is some special process in that building that needs water that hot. So you could consider lowering that set point to 120 or 130 degrees. And I guess it should be said that even if you do set that at 140 degrees, that doesn't necessarily mean they're going to get 140-degree water out of the sink, because most sinks blend some cold water with the hot water. The basis of savings by changing this set point is you are going to reduce the distribution losses in your pipes, because if you're putting hot water in the pipes throughout the building, if it's at 140 degrees Fahrenheit, that will lose more energy than if it's at a lower temperature. Just by the nature of heat transfer, you can reduce the delta T between the pipe and the surrounding space, you'll reduce your distribution losses. But this could possibly reduce your hot water use because that does limit the upper temperature at your sinks and showers. So if you get some people who just really like those super hot showers, you might be able to limit the hot water use a bit by changing the set point. And the savings, at least based on the distribution losses, that's all based on the delta T between the space and the water piping. So if you look at that delta T before, so say if you're starting at 140 and 75 for the surrounding space, so that would be delta T1, and let's say delta T2 would be 120 versus 75. If you can cut that delta T by some percent, then you're going to save that same percent on your distribution heating losses. Just because with that delta T relationship on heat transfer, it's a linear relationship. The water savings at the sinks and the showers, so this 0.2 right here, that's a little bit harder to quantify. There is something to watch out for. I'll have a diagram here in a moment to help illustrate this, but if you're going to mess with this set point, you only want to do it at what's called the thermostatic mixing valve. And we still want that hot 140-degree water within the storage tank. The reason why is to prevent Legionella bacteria. If you're not familiar with Legionella and Legionnaire's disease, there was something of a tragedy. I want to say it was in the 1970s, I think, but a bunch of people died as a result of this, and ever since then, Legionnaire's disease has been a big deal. So Legionella bacteria likes to grow in a temperature range of 70 to 120 degrees. It survives at 120, but doesn't multiply. At 130 and above, that's where it actually starts to die. What this thermostatic mixing valve does is it mixes hot water with cold water to deliver some actual water temperature that you want that is between the hot and cold water temperatures. And that TMV can have a different temperature set point than your storage tank. All right, so what does that look like? Here's a very basic schematic of a domestic hot water system. So if we're bringing in 55-degree makeup water from the city, which means we're also sending 55-degree water throughout all of this blue piping. So that cold water is also going to the sinks, to the showers. This is our mixing valve, which I'll talk about in a second. It's also going to the hot water tank to be heated. And let's say that water heater is stored at 140 degrees, nice and warm and hot enough to kill the Legionella bacteria. Out of that tank, you're going to get 140-degree water still. But you can see going into this valve assembly, so this is our thermostatic mixing valve. We have our 140-degree hot water in on one side, our 55-degree cold water coming in on the other side. We can use this valve to get 120-degree water to our end uses, which would be our sinks and our showers. So this thermostatic mixing valve allows us to deliver a cooler water to lower the set point that we're actually sending out throughout the building, but still maintain a very hot storage temperature. So what we don't want to do is change this set point right here. Instead, we want to change this set point. So you could walk into a building where they're storing water at 140 degrees, and the thermostatic mixing valve is set at 140, which isn't doing much good. It's not doing what it's intended and designed to do, but that could be an easy way to save some energy. You just need to make sure you're changing the set point at the right spot. And you might ask, well, what about all that water in the pipe at 120 degrees? Could that develop some Legionella bacteria? As long as the water is circulated often, doesn't get too stagnant, it's not really a huge concern. You also have to consider that water came from the storage tank, which was nice and hot, where it would have killed any Legionella bacteria right there. So it's not really a concern once you're outside of the tank and you've already heated that water up. But the reason I bring this up is this is an important example of how those good intentions, I'm going to come in, I'm going to save you energy, can have some unintended effects that aren't so good. Worst case scenario, somebody could die from Legionnaire's disease. So you'd have to be careful about where you're changing that set point. Today, it's really not a huge concern in a practical sense, as long as that storage tank is maintained at a nice hot temperature. But as a designer or an energy engineer who's going in and changing all these things on their systems, you probably don't want that liability in case something does go wrong. That's all I got today. Any questions? All right, we got about 20 minutes left, so I'll stick around, but otherwise have a good weekend, and I won't talk to you on Thursday, but let me know if you'd like me to show up on Friday afternoon for any office hours.
Thank you.
Thank you.
Thank you, Professor.